Hey, it's Peter here, and I'd like to talk about one of the more exciting things to come out of my lab recently. It's a little esoteric, so if you're in the machine learning field, you may find this very interesting, and if you aren't, it may be a little hard to grasp, but I'll try to explain it in a way that's fairly simple. Now, to qualify, this is an original idea in the sense that I came up with it myself, and I don't know that anyone else has come up with it yet. However, I would not be surprised if someone else beat me to the punch. So after I do this video, I'm going to do some research. I'm going to find out, am I really the first to come up with this? You know, it doesn't really matter because I get the sense of satisfaction whenever I come up with something new that, hey, I came up with that. But this is a really interesting thing, and it started as sort of a thought experiment, just sort of a what if. And it evolved into, the more I thought about it, I realized, like, holy crap, this has some applications, and it really does. So in this video, I'm just going to show conceptually how it works, and in the next video, I will show you implementation in software of the thing actually working. Now, this idea started off as a question: can we use artificial neural networks to store and retrieve data? It turns out the answer to the question is yes, as memories. You can train a neural network to remember things and then to recall those memories later. And the interesting thing is how it stores the memories. It doesn't store them as a computer normally would, where it's like, here's a byte, here's a byte, here's a byte in a linear order. It stores them in sort of a holographic fashion, where all the stuff is interconnected. And the more I thought about that, the more I realized that it can reference things, that if I saw this over here, I can reference the same thing over here. So rather than having two copies of the same byte, it can just go like, well, this is the same as this. So it has internal referencing in its memory structure, and that allows for efficient compression. In fact, it may even be the most efficient compression possible, although I'm not a mathematician, so I can't say that with any certainty. But it's very, very interesting. So how do you train an artificial neural network to store and retrieve memories or arbitrary data? Well, the answer to that is actually extremely simple, okay? You have your training data, which is labeled data, consisting of your X matrix and your Y vector. Y can also be a matrix, but for purposes of this, we're just doing it in a bitwise fashion. So you'll recognize these 4 bits as a nib, right? Like half a byte. So this nib here is exhaustive. I didn't write out every single possible iteration of it, but I've got the dot, dot, dot here. So we're going from all the way from 0, 0, 0, 0 to 1, 1, 1, 1. Now the number of possible combinations here is going to be 2 to the n, where n is the number of columns. Okay, so we've got 4 digits here. So 2 to the 4 is 16, right? So there's 16 possible combinations over here. Now this is an index. This points to your list, sort of like a memory pointer, pointing to where in the memory that data point is that you want to access, okay? Over here is the data point itself. This is your Y vector. So all you do, if you have, say, a multi-layer perceptron neural network, you take this data and you dump it into that. Now, what is this over here? This is just an exhaustive matrix of every possible index for that number of bits. So this actually never changes. Once you've picked the size of n, this is just, you just spit out this exhaustive matrix over here, that's X. Why? This is the data that you want your neural network to remember. You just feed your data in as a stream, just starting with 0, 0, 0, 0, you feed it in as a stream, and in this case we're doing it with just individual bits in the data, but you could put bytes in here as well, that Y could become a matrix. And your neural network then learns that whenever you give it a particular index value, it's going to output whatever is at that index. It doesn't store this data in a list like your computer hard drive would just have, byte, 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 or bit, 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 bit. No, it stores it in this weird, like, spider web of neuronal connections, but the data is there. So here we've got your stereotypical rudimentary multi-layer perceptron, and notice that the number of inputs here is 4, just like the last screen that I showed you where I was using a nib of 4 bits as the input, and their output is 1 bit. So this is a representation of a neural network that could be conceivably trained to do the function that I showed you on the last page. So you give in your inputs here that are either 1 or 0 to these 4, and they percolate through forward propagation. All of these little lines here represent weights or connections between these neurons. Each of these circles is a neuron. So, as far as how many neurons per layer and stuff, I'm not going to get into all that. That's a technical detail. But in this case, we've got 4 neurons in the first layer, 3 neurons in the second layer, 2 neurons in the third layer, and just 1 neuron in the output layer. So as far as the number of neurons to put in the middle layers, the hidden layers they're called, that's a whole other discussion. But the cool thing is that we at least know what our input layer size is going to be and what our output layer size is going to be, because we know presumably the number of bits that we need to index our data. So in this case, we're trying to represent 16 bits of data. So 4 bits will index that 16-bit heap of data. So this here is our index saying, which cell of data do we want to access. So we tell the neural network, let's say I want to access cell, 2, 0, 0, 1, 0. So we give it a 0, 0, a 1, and a 0. We forward propagate it, it chunks on through, and then it outputs either a 0 or a 1, depending on whatever it was trained to memorize as being in that cell. So if we look at this thing without forward propagating it, we just look at the neural net, where's the data in there? It's really well entangled. The data is stored in what are called weights. Each of these lines represents a weight, which is just a number that's being multiplied by the output of that cell. So this is an input layer, so these are just the numbers that you're putting into it. So then the first layer that's really processing something is this one here. So this is being multiplied by some number in this weight here, and it's being added here. This value here is being multiplied by some number that's in this weight here, and it's being added here. All that stuff gets added together. And then there's something called an activation function that it goes through, and that makes it nonlinear, and then it outputs it. Getting into the real nitty-gritty of how neural networks work is a little outside the scope of this. I highly recommend a Stanford course by Professor Andrew Ong. That's how I learned how to do all this cool stuff, and I would suggest you do the same. It's a really amazing course. Now, if you're thinking of using this compression algorithm, here are some of the features that it has. It can be lossy or lossless depending on the settings. So, for instance, if you were to give it a bunch of data, and then you were to say choose a relatively small neural network with few of those hidden neurons, then the thing would tend to be lossy, especially if the data was high entropy or very random, right? In contrast, if you were to use a big neural network on a relatively small amount of data, or you were to have data that was relatively predictable, had a very low entropy, like a lot of patterns in the data, then it would tend toward being lossless. But in all cases, you should be able to find a neural network such that the neural network is large enough that you get lossless compression. So it's just a matter of, what are you after? If you want it to be lossless, use a big neural network. If you want it to be lossy, or high efficiency, high compression factor, use a small neural network. You can specify the exact size of the compressed data. And how do I know that? Well, because the neural network stores the data in its weights. Those weights are stored in the form of matrices of floating point numbers. So those have a finite size, and you know exactly, based on the size of the neural network that you chose, you know exactly how much size that neural network is going to take up from the very beginning. So you can specify the size of your compressed data from the very start, and whether it's lossy or lossless is just going to depend on, how much are you trying to squeeze out of it. You know, how much data are you trying to squeeze through it, and how predictable or unpredictable is the data. Now, neural nets can be relatively slow to train, which means, you know, in the compression process here involves training the neural network. So that's going to be relatively slow. Using like graphics cards and supercomputers and stuff, you can definitely speed it up. But the plus is it's going to be pretty quick to decompress, because to decompress the data, all you have to do is forward propagate that neural network for every bit or byte, if you're doing it in a byte-wise fashion. For every chunk of the data, you just forward propagate the network. So that's a plus. Another plus is you can implement this decompression in hardware. So you can have a hardware neural network where you simply specify the weights, and then you just give it a value, you know, the index value, and tell it which cell in the data heap that you want to access, and it chunks through it and then goes, boom, this is what it was in that cell. So hardware implementations are desirable because they can be extremely fast. So you could put this into like a DVD player or a Blu-ray player, or, you know, some other type of device where it has dedicated hardware that is sitting there just spitting out, just decompressing the data continuously, and it can be done very, very quickly. And this last thing is speculation on my part, and I'm qualifying that here. This is complete speculation, but I speculate this could be the most efficient compression algorithm possible. Can I back that up scientifically, mathematically? No, not at this point. No, I can't. That's just intuition on my part. But because of the way the neural network works, because of how all those neurons are interconnected and all those cells are referencing each other, I really do believe that it has the potential to see every possible pattern in the data that may be present. So I do believe that this can be a highly, highly efficient compression algorithm. I can't tell you how efficient off the top of my head. You would need to either do a lot of calculations, or you would need to just do a lot of demonstrations to prove that. Now, one thing worth noting is the fact that if you're putting bits of data into this thing, but the weights of the neural network are these big floating points or double floating points, that does adversely affect your compression ratio, because you're storing these huge numbers that are your weights of your neural net. So that is something to consider. But do you have to use double floating points to everything? Maybe you don't. You know, maybe you could implement the neural network using integer math. I don't see why not. You could at the very least mess with those settings. So in the next video, I'm going to show you this thing working. I'm going to set it up in MATLAB, and I'm going to show you compressing and decompressing some data. And at this point, this is just an intellectual curiosity. I'm not going to patent it or anything like that. And guess what? You can't even patent an algorithm in the US. Algorithms are not patentable. So I am not going to try to pursue intellectual property protection of this idea. I'm just going to put it out there, and like I said, maybe somebody else already thought of it, but whatever, you know, at least I'm on record saying, you know, this is pretty cool. So stand by for my next video. It'll be a fun one. Cheers.